I'd like to begin this talk by asking you to look at these three images of isolated spindles. And the object here in the middle is a phase contrast image of the spindle. And as discussed in the phase contrast lecture, the contrast that we see, the dark contrast, is based on the difference in the refractive index, that being slightly greater refractive index of the specimen objects here, which most of these dots are clusters of ribosomes to the background. And these are the chromosomes at the metaphase plate. These are the spindle fibers here that make up the central spindle. And these are the astral microtubule rays at either side of this metaphase spindle. And on the right-hand side, which I have to move over here a little bit, this is the image of the same spindle that we see in polarization microscopy that we've discussed in the polarization microscopy lecture. And here those ribosome globs are invisible, and what we see are the submicroscopic contrast generated by the aligned microtubules that make up the central spindle fibers and the microtubules that are in the asters of the spindle. Because they're optically anisotropic, they have a refractive index for the electric field vibration along the axis of the spindle is greater than the refractive index for vibration in a normal direction. And this generates birefringence, which is turned into contrast in a polarizing microscope and that will become important in our DIC talk, because the DIC image that you see over here is actually made with a polarizing microscope. And so to understand DIC image contrast generation, you first have to have some understanding of how a polarization microscope converts birefringence retardation of two orthogonally vibrating waves into contrast, because that's used in a different optical configuration in DIC microscopy to make this image here, which highlights the edges of objects. And so if you look at the image here, you'd say, well, it looks like somebody shined a light from this side, and we have oblique illumination, and this clump of ribosomes here is scattering light off this side, but because the light is obliquely illuminated, it looks dark on the other side. And it turns out that that's completely wrong. That has no, the illumination of the specimen is uniform across the specimen, and contrast is not generated by a form of oblique illumination. But you can see that in this case, it's the edges that are highlighted and not just the mass of the object, such as in phase contrast. And the birefringence is not visible, but we do see the fiber structure of the clustering of microtubules in the asters and the clustering of microtubules that take place in the central spindle fibers. So I would like to ask you to sort of look at this image, which is a video-enhanced DIC image of individual microtubules that are only 25 nanometers in diameter. They're made out of tubulin dimers that are stacked head to tail into protofilaments, and there are 13 of these protofilaments here that make a cylindrical wall of a microtubule. And so those microtubules here are held on the surface of a glass cover slip by the motor protein kinesin that my host Ron Vale discovered and with his colleagues and using video-enhanced DIC microscopy in the middle 1980s. And this image is highly magnified, and as a consequence, it's a good one to ask about what the 6 major features are of a DIC image. And I want to start having you look at tiny particles like this one over here, and then there's another one down over here. Whoops, here we go. There's one right down there, and there's one right there. Right? And if you look at these tiny little particles, they may have a size that's even less than the microtubule, right? They all have the same sort of image structure. One side has got a bright spot, the other side has a dark spot. And if you look at each one, they all have a light dark spot lined up in the same direction. And that direction here is roughly running from about 10 o'clock to 4 o'clock, the axis that bisects the light and the dark spot. And that direction is called the shear direction of a DIC image. It's the direction of highest contrast, right? And the brightness of the bright spot or the dark spot depends on how much scattered light is produced by the specimen, which depends on the protein density there, and that could be different for the different little tiny spots. The protein density for the microtubules is fairly uniform along the length, and so the image that you see for microtubules looks rather constant along the length of the microtubule. But it differs for different directions. So if what these bright and dark spots are actually two airy disks. So the DIC image is made up of two, instead of a single airy disk defining each image point from a point in the specimen, there are two airy disks defining an image point from a single point in the specimen. And one of those airy disks is highlighted in normal DIC as brighter than the background, and the other airy disk is highlighted as darker than the background. So if you think about that, you could say, well, each one of these tubular dimers is scattering light. So if we look at a microtubule over here, I'm going to first point at this particle, and you can see it's black and white this way. And so if we look at this microtubule right here, you can see this edge here on the left is black, and this right edge is white. And all along the length of this, right, we have black, white, all the way up to this point here, which probably it came up off the cover slip, so you don't get to see it. All right, and so it's just simply that all these individual scatterers here are all producing this paired white-black image. They're all stacked linearly on each other, and that then defines the axis of the microtubule. Okay. On the other hand, if we go look at a microtubule that's oriented in the direction of this shear direction between these two airy disks, and there's one right here, see it? You can barely see the microtubule, and that's because black then overlays white, overlays black, overlays white, overlays black, overlays white, and the net sum of those two, right, when added together gives you very little contrast relative to the background. So contrast is maximal in the direction of shear. Right? If we look at this larger object over here, right there, which is a blob of membrane or a vesicle of some sort that's settled on the cover slip surface there in this preparation, you can see that the right edge, again, is bright, the left edge is dark, but in the middle, you have the same intensity as the background light. So what is highlighted is the edge, not the middle. And again, we can take the same analogy here. If you take one of these particles, right, and think of that as like a unit scatterer in this vesicle right here, we still have black, white, and then here, all of a sudden, we now have black and white overlapping each other, overlapping each other, overlapping each other, overlapping each other, right? So we get the same contrast as the background. And then finally, when we get to the left edge, we now have blacks that don't have corresponding whites to overlap them. And so on the periphery of the left edge, we now get black contrast, right? So fundamentally, it's the same mechanism that generates contrast of this tiny little point here object is the same mechanism that generates the edge contrasts that you see in the DIC. So then we need to understand how those two images are made, how their contrast relative to the background are generated, and how this is done in the polarizing microscope. And in the next slide here, I've summarized the major features again that we've just discussed, which is contrast is directional. It's a maximum in one direction, a minimum in the orthogonal direction. Contrast highlights edges, uniform areas have brightness of the background. In the direction of contrast, one edge is brighter, the other darker than the background. Each point in the object is represented by two overlapping airy discs. In the image, one brighter and one darker than the background, the way DIC is normally set up to be used. The direction of the airy disc separation, this light-dark pair, is the shear direction, and the direction of maximum contrast. The peak-to-peak separation of the two black-white airy discs is the amount of shear, shear being the term for the separation of those two images, and it's typically chosen to be about a half, sometimes two-thirds, but usually a half of the radius of the airy disk, so that you can approach the maximum resolution possible of the objective, even though you're making up the image out of two airy disks. Okay, so how do we make such an image? So a DIC microscope is a polarizing microscope. So to understand DIC, you need to understand the fundamental aspects of polarization microscopy. So before you go any further in this talk, you really need to go back and listen to the talks that were given by Shinya Inoue and by myself on polarization microscopy. And I'm assuming that you've listened to those two talks and what I'm going to say now. Okay. So to set up a microscope for DIC, what you're really doing is making a dual beam interferometer in which the two beams are very close together. That is, in a sense, they're only separated by that shear amount, right, that will eventually produce those two overlapping airy discs. And this is done by aligning your microscope and objectives and condensers for curler illumination. And then, in addition, you have the normal setup for polarization microscopy. We have a polarizer near the condenser diaphragm plane. We have an analyzer above the objective, back focal plane and aperture, where you can get it in and out of the microscope path. In addition, there's a compensator used in the system that can either be before the analyzer or just after the polarizer. And that is a birefringent retardation plate that can be used to advance one of the used in the system, which I'll describe here, I think, a little bit later. And then, in addition, there is a condenser DIC prism that's going to split the initial beam of light into two beams that are going to pass through the specimen. And then there's a conjugate DIC prism for the objective that will recombine these beams and then send the recombined beams through the compensator and then the analyzer, and then contrast will come back up with the analyzer. So the contrast that you get out of this system here depends basically on how we get contrast from birefringent retardation in polarization microscopy, which is why you need to look at those other two lectures. Right? And so how do we make the two beams? And this is done with the DIC prism in the condenser. Initially, one version of the DIC system, when it was first invented back in the 60s, used what's called a Wollaston prism, and this was put in the condenser front focal plane. And this one is made out of quartz, which is a birefringent crystal. And being birefringent, it has two refractive indices. One of them here, I've shown for the upper wedge, has its vibration axis this way, and the other one's going to be into the board. And these two wedges are cut so that they're what's called the optic axis of the crystal, and in the case of quartz, it's the axis that has the extraordinary refractive index, and has an electric field vibration in the direction of this axis, and it's a larger value for quartz. compared to the one that's perpendicular to it, which is shown here by a dot, which is the would be called the ordinary ray for quartz. So on the bottom wedge, I think, is where we define these things. And so for the bottom wedge, this axis of symmetry is into the plane of the board here, right? And so what's called n sub e value in the direction of the axis of symmetry of the quartz crystal is into the board, and that's this one, and that has a higher refractive index. And the n sub O value for quartz, which is produces a wave perpendicular to it, is in the plane of the board. And these prisms in the microscope are inserted into the microscope at 45, with their axes at 45 degrees to the polarizer direction. So in this drawing, I've put the polarizer, polarized light coming from the polarizer here at 45 degrees to the direction of these vibration axes in the crystal. Now, when you take plain polarized light and coming along through space and you hit a birefringent crystal, instantly the energy from the electric field is resolved into two orthogonally plane polarized light beams, one vibrating in the n sub e direction and one vibrating in the n sub O direction, right? And so for the bottom quartz wedge, if I start with plane polarized light, and I'm going through air, which has a low refractive index, and I hit the crystal, then once I'm in the crystal, the frequency of vibration is the same because it's transparent, but one wave goes slow and the other wave goes fast. The slow one has the higher refractive index, and the fast one has the smaller refractive index. And I've shown that in the drawing here by this dot here is the wave that's vibrating into the board, and it's going slower compared to the wave that's vibrating perpendicular to that. These two vibrations are orthogonal to each other, and electric fields that are orthogonal to each other cannot interfere. So we're generating across this wavefront here, coming from the polarizer, by using this first wedge, is we're generating two orthogonally plane polarized light beams that are vibrating, the electric fields are vibrating in the direction of the crystallographic axes, right? And in the lower wedge, you can see the n sub e one is slow compared to the n sub O one. And then we hit the wedge boundary, in which the axis directions of the crystal are reversed. This causes refraction at the boundary, so that the wave, one wave is bent away and moves off to the right. That's this one here. And the other wave is bent the other way and moves off to the left. And so this looks like the two wavefronts then diverge from each other based on the angle of this wedge and on the differences in the refractive index, right? So what we have coming from the wedge are these two wavefronts. There's one I've drawn here that's going, let's see if I can do this here. This is a little hard, but you can see one is tilted to the right, and the other wavefront is tilted to the left and heading out towards the condenser lens as it moves away from this Wollaston prism. Now, in the microscope, we'll consider first this lower drawing. We'll consider the wavefronts that are coming right from the center of the prism, in which the thickness of the lower prism is equal to the thickness of the upper prism. And because those two thicknesses are the same, even though the wavefronts are diverging from each other, they are in phase with each other. Okay, so that in terms of their propagation coming, I've got to actually do it this way, in terms of their propagation going through the microscope. So you can see that the dot here for this wavefront and the bar here for that wavefront are actually right in line with each other. But if we go to the top of the prism, because the lower prism is thicker than the higher prism, then one wave gets way behind the other wave, right? But because they're coming from the, and then you'd have the same sort of drawing, but equal and opposite for the other end, for the other side of the prism. But I only drew just one of these. But note that for both of these waves, this one here, and the one coming from near the outer aperture of the entering into the outer aperture of the condenser, because they're coming from the front focal plane, they then get converted into parallel beams that move through the specimen, and those beams are separated by the shear separation as reflected into the specimen plane. And that'll be roughly the same for either whether it's this parallel beam or whether it's a high numerical aperture beam that's moving through the specimen. Now, the objective and then the objective prism are chosen to be conjugate in effect to produce an equal and opposite effect than what was done here by the condenser prism and the condenser lens itself, so that these two beams are then focused back together again at what would be the back focal plane in this alignment, right? And then what happened here, what happened to the two beams up here, you get an equal and opposite effect here. And if everything is perfectly matched, and I'm going to have to move my finger this way, right? Everything is perfectly matched. The two beams will come out, although vibrating orthogonally to each other, exactly in phase with each other. This will be true for here, this will be true for here, this will be true for here, true for here, if everything is equally matched. And so, as we'll talk about in a little later, DIC prisms are selected so that they match each other in order that you can get a perfect match and be able to extinguish the light, or have these two beams be in phase with each other all across the aperture of the objective, right? Now, these beams then hit the analyzer, and which is this next guy right here, right? And if they're in phase with each other, then what you end up having is the same initial plane polarized light that came out of the polarizer. And because the analyzer transmission vibration direction is perpendicular to the polarizer in the way we align the DIC scope, it will essentially allow, these two beams will interfere with each other, but give no net light transferred through the analyzer. And so we say that the light has been extinguished, right? Because both of these beams suffered the same net retardation, or they have the same optical path going through the specimen, and the prisms did an equal and opposite advancement or retardation of the two beams as we went through, right? So to see what happens if we put a specimen in there such that we modify what happens to one beam relative to the other by changes in the optical path, I've made up a specimen down here, which is sort of trapezoidal in shape, and it's got a refractive index larger than the background, and I've defined regions A, B, C, and D, and then I've only considering the beam that's coming right up along the optic axis, and for this case, the O wave is drawn as a semi-dotted line here, and it's been translated to the right-hand side, and the E wave, which is a solid line, is translated to the left-hand side, as you can see way over here, right there. See, E wave ends there, the O wave ends there, right? So that's the wavefront that's going to come down the microscope axis, come through up through the specimen, and as that wavefront just passes through the specimen, because this has a higher refractive index, both wavefronts are going to be slowed down because of being in the specimen, and they'll be slowed down in proportion to the refractive index times the thickness of the specimen, right? So it's the thickness of the specimen times in parenthesis, the refractive index of the specimen minus the refractive index of the background. And so you can see this is sort of an embossing of the shape of the specimen on the two wavefronts right there. So those wavefronts are then collected by the objective and then pass through the objective Wollaston prism, and the objective Wollaston prism realigns the wavefronts to each other. And you can see the O is shifted to the left, and the E is shifted to the right. And for me, shifting to the left is not easy to do, so I'm not going to do it. But you can see by looking at the endpoints of these lines right there that they're now lined up here. And then over here, they're now lined up. But look what happens at the edges. That shifting by the objective Wollaston prism shifts the retardations of the edges for the two wavefronts away from each other. So now that where we had edges, we now have a retardation difference between the two edges. Now that each of these, the E wave and the O wave, these orthogonally vibrating waves that go through the specimen, right? However, go through the prisms and the specimen and so forth, right? They have the same amplitude, but at this stage, in the background, in the region corresponding to A, they have no retardation difference. So when we go to A, which is over here, right? Because there's no retardation difference, we get plane polarized light, which is canceled by the analyzer, and we get blackness. But at this edge, there is a retardation difference between the two waves, and so that retardation difference allows light to get through the analyzer, and we see a bump at B, right? At C, where we had a constant thickness of the specimen, there's no retardation difference between the two wavefronts, and so for C here, you can see that we go back to having the same intensity as the background at A. And at D again, we now have a retardation difference. And so at D, we now have a bump again. And then now we get back to the background over here, and we go back to being black again. So this is a dark field microscopy made in DIC, right? And it's not a very easy image to look at, and it's a very dark image. And so we normally use a compensator in the DIC microscope to advance one of the wavefronts over the other in order to brighten up the background. So if we go back, here we've got the embossment that takes place at the image. We now, down here. Then we go through the Wollaston prism. We now have realigned the two wavefronts, but at the same time as we realign the two wavefronts, we've split apart the images of these of the edges, right, which is what produces the two airy discs, right? And this will now show you why one is dark and one is white. So in the images that we were analyzing to begin with of the microtubules and the particles, we had a compensator in the light path, and the compensator was adjusted such that the right-hand edge here, we were advancing one of the wavefronts over the other so that the right-hand edge essentially has no retardation difference. But the background, if you look here, or you look at constant regions of the specimen, or if you look at the background over here in A, they all have the retardation that's been produced by our compensator, and as a result produce light. So if we come way over here and go up through the analyzer, that retardation produces light, right? And in fact, it further advances the retardation difference between on the left-hand edge, so we get a brightness that's brighter than the background for the left-hand edge. Then in the constant region of the specimen, we get the background light intensity again, and then on the left-hand edge, because there's no retardation difference, we get darkness, and finally we go back to the background level of intensity. And that's what produces the light-dark image in DIC microscopy. Now, compensators can be used in both additive and subtractive mode. You can reverse whether or not you advance the E wave over the O wave or you advance the O wave over the E wave. And by doing that, you can decide to make the left-hand edge dark and the right-hand edge bright. And in fact, that will produce the same sort of image, and we've done the same thing, except for we've made the two wavefronts actually become in phase with each other on the left-hand edge and enhance the retardation of them here on the right-hand edge. What kind of compensators are used to do this? And in the original designs for DIC, one was called the Smith design, which used these Wollaston prisms, and they were actually built into the objective in the objective back focal plane. So when you bought the objective, it said DIC, and it had the prism in it. So you couldn't use the objective for other things because the prism was built into the objective. And the Wollaston prism for the condenser pretty much could be put pretty close to the condenser diaphragm plane. So that wasn't necessarily built into the condenser. But because this was built into the objective, and this was to some extent stationary in the condenser, there was no other way to be able to change the retardation of the E and the O wave for compensation purposes. And so an additional compensator is added to the system, and that's typically a Descendamont type compensator, which is made out of a quarter wave plate retarder and a rotatable polarizer, or a quarter wave plate retarder over here. It can be put over here, and a rotatable analyzer. And the combination of those two allows you to rotate the polarizer or the analyzer, and it turns out the amount of retardation between the two orthogonal wavefronts is proportional to the degree of that rotation. So, and in fact, nowadays, Descendamont compensation is very commonly used in polarization microscopy. Normarski modified the design of the Wollaston prisms, make the axis of one of the wedges different, and this allowed to put the prism outside of the objective. And in Zeiss's initial and they still do this in Zeiss in their initial implementation of this, because this is outside the objective, they could then put a mechanical screw mechanism on it and translate the Wollaston back and forth to either positively or negatively compensate the advance or retard the E and the O waves relative to each other, and you didn't need the Descendamont compensator. And nowadays, it's still basically the two kinds of schemes that are used. Now, the Normarski prism, as I mentioned earlier, has one of the wedges cut with the optic axis, crystallographic axis of the wedge at an oblique angle, and that was a clever thing on his part, because that then put the effective focal point for the prism where the two beams, the E and the O beams, would come together into the back focal plane of the objective, while the prism itself was outside of the objective. And then the same thing was done on the condenser side, so you didn't necessarily have to have the prism right exactly at the front focal plane of the condenser. Now, there are other schemes for how to build these prisms today that the different manufacturers have developed, because there's licensing problems, right? And so you can kind of get to the same result as I diagrammed here for the basic concepts, but use slightly different prism arrangements, but the overall effect of it is the same effects that I've described in image formation. Okay, now the addition of retardation between the two beams, either in the plus or the minus direction, is kind of the equations for it are down here, because the prisms and the compensator have the crystallographic axes at 45 degrees of the analyzer or polarizer direction. then the equations for the intensity through the analyzer are given by this sine squared of the retardation of the compensator plus the retardation of the specimen edge divided by 2. And the background light intensity is just the sine squared of the retardation of the measured in radians. That's what delta means, measured in radians divided by 2. And so I made a plot here of this sine squared function. The solid line here is the background light intensity, and the dotted line is the intensity for an edge. And if this is the right-hand edge, it's brighter than the background. And if it's the left-hand edge, you can see over here that it's darker than the background. And this is the variation that you get in light intensity as you add more or less compensation. Now, it turns out that with our cameras and the way they work, it's usually best to get the highest contrast is to take one of the edges and makes it maximally dark, and then use your contrast enhancement capabilities of your computer or camera or electronics to brighten up the bright side of the image. And that's the way this image was done here. And it took about a 1/10 of a wavelength or 1/20 of a wavelength of retardation in green light, 550 nanometers, to make this image of my cheek cell. And now you can see that there are no halos anymore. We have the dark and light edge of the nucleus, and we now can start to see a lot of the very fine structures, the tiny little particles, and so forth and so on, that high resolution DIC offers us.